On June 12, 2026, emergency export controls executed by the U.S. government severed global access to primary AI models overnight. That immediate blackout exposed a brutal engineering reality. Treating a single AI provider's API as standard software infrastructure is a fatal flaw. For 19 days, enterprise ecosystems depending entirely on that centralized intelligence froze simultaneously. While the broader tech industry scrambled to repair the loss of this monolithic platform, a highly resilient, decentralized architecture was quietly proving its viability in the dark. API access can no longer be modeled as guaranteed compute. It is a highly volatile geopolitical asset that can vanish without warning. This table captures an anomaly from the blackout. A multi-agent orchestration model, Sakana Fugu Ultra, survived the ban and outperformed the locked-down frontier models. It achieved 73.7% on SWE-Bench Pro and 93.2% in LiveCodeBench, defeating both GPT 5.5 and Claude Opus 4.8. Mathematically, a fragmented network of smaller, open-source models should not be able to defeat a massive, unified frontier model. We have to ask how this swarm architecture actually processes information, and why this seemingly inefficient setup is now a mandatory requirement for large-scale enterprise deployments. We will deconstruct the specific mechanics of swarm orchestration to show how it transforms raw operational inefficiency into structural geopolitical insurance. The traditional monolith on the left is a centralized brain, a single point of failure. The swarm architecture replaces this with a lightweight orchestrator. This node doesn't compute the answer. It dynamically breaks complex tasks into fragments, delegating them to a network of specialized nodes. The orchestrator then waits for those disparate models to process their individual pieces, collecting and synthesizing the outputs back into a single cohesive response. This dynamic routing serves as active, localized defense. If a specific government restricts a single node, the orchestrator automatically routes around the localized damage without causing a system-wide failure. Enterprise-grade resilience now depends on structural decentralization, entirely separate from raw baseline model capability. Even when global access is fully restored, relying on a unified monolith comes with severe internal operational constraints. This flowchart maps the fallback trap. Hyper-aggressive safety classifiers frequently intercept standard workflows. A benign code review triggers a false positive, causing the system to silently override the request and force a downgrade to an older, less capable model tier. Alongside this functional unreliability is a steep financial penalty to access the actual frontier tier. Enterprises forced out of basic tiers and into strict pay-as-you-go frontier access face an immediate 500% spike in costs. Providers are also layering in new passport gatekeeping protocols, adding heavy identity verification and compliance friction to basic API requests. Between internal safety triggers and predatory pricing, the monolith is entirely too volatile for unoptimized, large-scale enterprise use. Achieving the geopolitical resilience of the swarm brings heavy operational burdens. Because the orchestrator must make parallel API calls to multiple external nodes simultaneously, latency increases by a factor of 4.5, and raw operational costs multiply by 5. There is also the added complexity of black box compliance, as dynamic routing obscures exactly where specific data packets are being processed at any given moment. Managing these orchestration costs requires strict task triage. As shown in Phase 1, high-cost models are isolated for long-horizon architectural planning. Following the flow into Phase 2, mechanical execution and basic coding are aggressively offloaded to cheaper legacy models. Treating every engineering task with equal AI priority under this architecture will result in instant budget exhaustion. To offset the massive orchestration tax, aggressive prompt caching is required, yielding up to a 90% reduction in input costs for repetitive codebases. The secondary tactic routes non-real-time tasks through asynchronous batch APIs, cutting operational costs in half. Engineers must also implement an anti-friction layer explicitly designed to combat false positives from hypersensitive safety classifiers. This programming automatically detects unjustified network blocks, terminates the request, and immediately reopens the session wrapped in a neutral context to navigate past the triggers. Finally, the system requires a physical portfolio approach. Risk is mitigated by dynamically mixing US, European, and Japanese open-source models directly within the orchestration layer. Modern enterprise AI deployment requires building automated systems that actively outmaneuver hostile infrastructure. This isometric blueprint reveals the macro picture of our physically segregated, multi-layered global network. Generative AI has transcended pure software engineering and operates squarely on the front lines of geopolitics. Architects must now design for extreme operational friction, factoring in sudden national export controls and stringent passport-level identity gatekeeping. Extracting sustained business value from frontier models requires completely abandoning the assumption of a reliable, frictionless API. Corporate survival dictates building decentralized, multi-model infrastructure that treats sudden, cataclysmic platform failure as a baseline expectation. If the infrastructure of the next decade is this fragmented, how much of your codebase relies on the false promise of a permanent monolith? Until next time, we'll keep breaking down the theory so you can build the prototype.